Hi everyone, I'm Xiaoting Peng from UAUC, and this is our work, Tactile-Based Human Intent Recognition for Robot Assistive Navigation. So this work is about helping people with limited mobility, such as older adults. And we noticed that when they are working with a caregiver, they typically apply some specific grasping pattern on the caregiver's arm, such as a pull for stop and a twist for turning instead of directly talking to them. So in this work, we want to replicate this intuitive and natural interaction with assistive robot by designing a tactile skin. So the assistive robot, we use stretch 3 here, can feel the user's grasp and thus recognize their moving intent and provide support. This is an overview of our system. It consists of like the hardware design and some algorithmic contribution and put together into a system. So on the hardware part, we utilize a three-layer tactile sensor design proposed by Professor Wenjin Yuan's group. And this sensor is fixed on a cylindrical holder and then mounted on the arm of the stress-free robot. And here we provide an example of the mean tactile pattern from one user. So first, we admit that we cannot collect much data from older adults, so we choose SVM, which is simple yet effective for small amount of data. However, we notice that users sometimes exert slight rotational shifts along the cylindrical parameter, but traditional classifiers most ignore the topology of this cylindrical sensor and thus achieve low classification accuracy. So in this work, we propose SVM, which changed the RBF kernel to include two different distance measurements, like these two different penalties. So here we provide an illustration, giving a reference signal. If another signal has a similar pattern with this small shift, they will be in the same class. However, if the pattern is similar but has a larger shift, they will be classified as a different intent, as well as if the activation shape is different. For more details of this method, please refer to our paper. So with the sensor and algorithm, we integrate into a real-time system called TacNav, which takes the raw tactile data in a sliding window form and extract features and classify with sticky SVM. We also add an output buffer to stabilize the prediction to improve the system robustness. Finally, the intent output is communicated to the robot with ROS2, and the robot provides real-time mobility assistance accordingly. Next, we demonstrate our real-world experiment, which contains a human participant getting a cup of water and return with the robotic mobility support. So on the top is our TechNav system, and on the bottom are the two baselines, one using joystick to control the movement, and the other one use voice commands to control the robot. Yeah, we can see with our system, the user can complete the task much more easily and also efficiently. Yeah, I will skip the rest. And here are some evaluation results. We tested our CKSVM against other classifiers on both simulated and real-world collected dataset, and our model consistently outperforms other baselines. For user study, our system also gets higher rating in 5 out of 6 metrics, showing a preference for our system over other baselines. Thank you.